We have seen that a sinusoidal source produces a sinusoidal response. So that's what we did in the last example. Input function was a sinusoid, or output current was a sinusoid. But note that the phase shifts of the two could be different. Okay, the inductor in the last problem generated a phase shift that was proportional to, or that was dependent upon the frequency, the inductance, and the resistance. So likewise, a complex source is going to produce a complex response. So let's just imagine we have a source that is a summation of a cosine plus a sine times an imaginary number. Okay, so recall back to our review of complex numbers at the beginning of the course. This type of source will also produce a sinusoidal complex response. So summation of a cosine and a sine times an imaginary number with different phase shifts. The reason that this is important is because we have this fantastic identity called Euler's identity, where we can relate this summation of these two sinusoids times a complex number to what we call a complex exponential. So this Vm cosine omega t plus theta plus j times Vm sine omega t times theta is equivalent to Vm times e raised to the j times the quantity omega t plus theta. The reason that this is desirable is because the solving of the differential equation represented by circuits that include capacitors and inductors in them is much easier with exponentials. So what we're really going to be doing is, given our initial problem of solving the circuit for Vs equal to Vm cosine, what we're actually going to end up solving is Vs star, which is equal to this complex exponential. And then when we're done with it, we know that the solution is going to be a summation of a cosine and a sine times an imaginary number. So what we're going to do is take the real part of that solution, which is shown here, the real part of that complex exponential, which is going to get us back to the desired quantity of I as a function of time. So rather than solving for IT directly through differential equation of sinusoids, we're going to solve for IT star through differential equations of complex exponentials and then convert back. So let's do that. We're going to now take the circuit, the original circuit again, where V is equal to Vm cosine omega t. What we're going to do is instead is solve Vm e to the j omega t. Note that I don't have a theta offset here because my initial problem had a phase shift of 0. So our KVL then reduces to Vm e to the j omega t equals to Vr plus VL. Sub in those IV relationships just like we did in the last problem. Now the power here is that we know that the solution of I is going to take on the form of a complex exponential with a different phase shift phi. So we know that I is going to look like Im times e to the j omega t plus phi. So subbing that form of the solution into the problem, we get this expression here. And then simplifying, we get Vm e to the j omega t times Ri e to the j omega t times e to the j phi. Just recall that e raised to a power that is a summation of powers can be split as e to each individual power multiplied by e to the next some power. Plus, again, we have to take the derivative of I e to the j omega t plus phi, which is going to be j omega times I times our L, which is out front, times e to the j omega t e j phi. Note at this stage we can see that each term has the e to the j omega t present in the term, so those are all going to cancel out. And this reduces to Vm equal to Im e to the j phi times quantity R plus j omega L. Note that this is an important stage. The first thing to note is that our variable t got canceled out. We don't have time as being a variable in the problem anymore. This is interesting, and it effectively, we just were converted from being in the time domain to something else. In fact, this is what we call the frequency domain. And if we look at the solution, we see that the angular frequency, omega, is what our independent variable is now. that and the phase shift. So this form now of our solution is what we call frequency domain. Time is again irrelevant because we note that the sinusoid is repetitive in time. It repeats every period t. And so the complex exponential is useful firstly because it helps us get rid of that variable t, noting that this can be expressed as a summation of sinusoids which just cancels out. And so now we take this form and we solve it for Im e to the j phi because that's what our solution is, and we get Vm over r plus j omega L. This is our solution in what's called frequency domain. Now note that this is a complex number and it's in the form that is rectangular form. It just maybe doesn't look convenient because it's not a plus jb and we don't know what a and b are just yet. So let's convert this solution, Vm over r plus j omega L, to polar form. We can do so by multiplying the numerator and the denominator by the complex conjugate. Performing that algebra, we get this solution, Vm r over r squared plus omega squared L squared minus j times omega L over the same denominator. So now this is in rectangular form. That looks like a plus jb. So we can plot this on that complex axes where the x-axis is the real and the y-axis is the imaginary. So there's a, there's b. So we're looking for the length of this vector r and the angle phi. Converting this rectangular number to polar form, in other words, gives us that the solution of Im e to the j phi in polar form is Vm over the square root of r squared omega squared L squared times e to the negative j arctangent of omega L over r. This should start looking familiar given the solving of our last problem. But now we've got the rectangular form of the solution to the polar form of the solution to now the complex exponential form of the solution. Just three different ways to represent complex numbers. The polar form of this shown here is probably the most useful because once we get to this, we can easily convert to time domain by just taking the magnitude and the phase angle and then plugging that into our cosine form in time domain, where conversion to time domain is really taking the real part of that complex number, I, which is the solution that we actually solved for, so our solution is shown here on the bottom. Note that this is exactly the same solution that we found with using differential equations in the time domain. So this abbreviated complex representation that we saw on the last slide is what we call a phasor. So a phasor is simply a vector, and it's characterized by two parameters, an amplitude and a phase angle. Note we don't need time. So when we represent things with phasors, in other words, a sinusoid with the phasor, this is what's called a frequency domain concept. Time is not a variable. Omega and phi or theta are our independent parameters. So we're going to do a few examples of converting time domain signals into phasors. For example, if we have a voltage source equal to V cosine 100t volts, all we need is the amplitude and the phase angle of this. So in polar form, the phasor V, note that we're going to represent that as capital V with a bar on top of it, denoting that we're representing the frequency domain phasor of the voltage source V, is going to equal to 5 with an angle of 0 degrees. And that's in polar form. In rectangular form, that would be 5 plus j0. And in exponential form, that would be 5e raised to the j times 0. Let's do a couple more examples. You might want to, at this point, pause the video and make sure you can do these examples before listening to me. So let's convert the time domain signal 100 cosine 400t minus 30 degrees into a phasor. First thing we do always is convert to cosine first. We're in the cosine form right now, so all we need is the magnitude. So phasor V is 100 at an angle of whatever our phase shift is inside of our argument of the cosine, which is minus 30 degrees. So in our second example, we start with a value of negative 5 times the sine of 500t minus 110 degrees. So what we're first going to do is convert that to cosine. So that's negative 5 cosine 500t minus 110 minus the shift occurred by converting to cosine, which is 90 degrees in the negative direction, or a shift shift towards the right. And summing those, we get negative 5 cosine 500t minus 200. Note that this is the same thing as, right, if we want to get rid of the negative sign, we could write this as positive 5 cosine 500t minus 200 and plus 180 degrees, because 180 degree shift, plus or minus actually, will convert from positive to negative given our trig identities. So we have two forms of the solution here, negative 5 at an angle of negative 200 degrees, or positive 5 at an angle of negative 20 degrees. These are equivalent solutions. The preferred way to write this would be the bottom form. So negative or positive 5 at an angle of negative 20 degrees. That's because we usually want to represent the phase angle as the smallest angle possible, at least where the phase angle is going to be less than 180 degrees or greater than negative 180 degrees. But just because we know that the sinusoid repeats every 360, so keeping the phase angle within that range is usually desirable.